Okay, everybody, we're gonna start today. Let me turn it up a little bit. All right. So we're gonna finish chapter 4 today, which is the chapter that covers various aspects of structure and bonding in covalent compounds. And then starting Wednesday, we'll see a pretty big transition. Now, one announcement that is sometimes a frequently asked question at this point after the first exam. You may have noticed that in Canvas, there's now what's called a makeup exam. Just to be clear, that's only for people that missed the exam for a valid documented reason. So you have to have communicated with me about that. You have to sign up in CASA and be given permission to do that. And you have to take it in CASA. So unless you've talked to me about the makeup exam, don't try to take it. It won't work for you. Okay? So that's what that's for. The first time you've seen it. Again, it's only for those limited situations when you miss the exam for a valid documented reason. All right. Now, speaking of the exam, some of you are probably wondering how it went. For others besides yourself. So this is a summary of our results from this semester. Almost identical to last semester. So our average was a tick higher, 61.8%. And then last year, this time, it was 61.3. So not a really significant difference, I would say, but at least a little bit better. And there was one student in the class who got a perfect 22 to 22. So congratulations to that person who will remain unnamed, but can feel proud nonetheless. And you do notice that there's a pretty big drop from, well, 2023, which was, and then I had a gap in 2024. But between these two semesters, we did see a drop in exam averages when we switched to WebAssign. I don't know if the reasons for that are entirely clear. So these averages were from the previous exam system. This is when we switched to WebAssign, dropped a little bit. But at the same time, we made the homework count for a higher percentage of your grade, and we made the grading scale easier. So the overall grade distributions in terms of how your final grade looks out are, if anything, more favorable than they used to be. So don't really worry about that comparison too much. That's why it happened, but you should mostly be focused on, of course, your own expectations, how they compare to what you did. And if you want to go over your results in any way, or if you want to talk about strategies for improving your score in the next exam, if that's something that you think you want to do, I'm happy to have those conversations either regular office hours today and Wednesday after class, or anytime we can find a time to meet and talk about that. All right. So there's still a lot left to go in this semester. So even if you're not thrilled with their first exam results, it doesn't tell the whole story for your whole semester necessarily. All right, but as I said, the main topic for today is to finish chapter 4. Now, at the end of the last lecture, we just started introducing some of the concepts associated with molecular orbital theory, which is the more complex bonding theory that we're going to sort of finish up with in this course. So the idea again was that in molecular orbital theory, we're taking atomic orbitals from each of the two atoms. We're only going to be talking about molecules that are diatomic, just two atoms bonded to each other in any level of detail. And you're taking atoms that are bonded to each other, and you're taking their atomic orbitals and mixing them together to make new molecular orbitals, which are orbitals that are delocalized over the entire molecule, and that are then going to contain the valence electrons that are responsible for bonding in those molecules. So we're going to start with 1s orbitals. So we're going to start with H2 or other small molecules that would only have 1s valence orbitals. And there's really two types of molecular orbitals that always form, as we talked about last time. So the first of those is the bonding orbital, which is an in-phase or additive combination. So at a very simplified level, we'll call this sigma. So we use the sigma and pi labels, which mean the same thing that they basically did when we introduced them earlier in the chapter, different types of bonds. 1s orbitals can only make sigma bonds. And so the bonding orbital would be just an in-phase combination of two 1s orbitals, one from each atom. And so then what that looks like, again, the idea here is that we no longer have separate 1s orbitals on each atom. We're combining them to make new molecular orbitals. And so the bonding molecular orbital, we have the nucleus here and here, is going to be sort of just a delocalized sigma orbital that goes over the entire molecule. Again, no longer one orbital here, one orbital there overlapping, but an entirely new orbital that's delocalized over the entire molecule, and that's what we call the bonding orbital. Now, the other thing that happens, though, whenever two atomic orbitals combine, they can make in-phase or out-of-phase combinations, and both of them have to occur. So the out-of-phase combination, which is referred to as the antibonding orbital and abbreviated here with a little asterisk, sigma star 1s, is just the out-of-phase combination of those same 1s orbitals. Now, what that looks like here is what we're going to have is the greatest electron density is going to be outside the nucleus, and because the two orbitals are added out of phase, you're going to have sort of one phase there, opposite phase on the other side, and you're going to have a node in between. So as we kind of talked about in abstract last time, when you populate antibonding orbitals, that would result in weakening the bond. But with 1s orbitals, that's really all you have to worry about because there's only going to be the in-phase and out-of-phase combinations. Nothing else would be possible for those if you're just talking about a pair of 1s orbitals. Now, the more important thing to internalize, rather than the shapes of the orbitals, even though that's I think useful to think about, is what does the orbital energy level diagram look like? This is what we're going to be talking about the most today, and having to understand how do we use these diagrams and how we apply them. So the way that we draw these diagrams, if we're trying to be as complete as possible, is that on the outsides of the diagram, we're going to have the atomic orbitals that are mixing, in this case, two identical 1s orbitals. And then again, when those orbitals mix, they're going to form a bonding orbital and an anti-bonding orbital. Something else that we briefly introduced last time is that the bonding orbital is lower in energy, so we would draw an orbital down here in the middle. So the middle part of the diagram shows the molecular orbitals that form when the atomic orbitals are mixed. So that's going to be our bonding sigma 1s. And so again, what we have here is on the outside are the atomic orbitals shown. And then here in the middle are the molecular orbitals. And then the antibonding orbital is higher in energy than the atomic orbital, so you're going to draw that up here. So you get this splitting between the bonding and antibonding orbitals that we'll always see. And that's what the diagram would look like. Now, it's useful, again, to understand the diagram, and I think including all these pieces shows you nicely the atomic orbitals that all these molecular orbitals come from. The part that's most important from an application standpoint and from a problem-solving standpoint is just to be able to remember and recognize the ordering that these molecular orbitals come in, which again, for orbitals derived from 1s is very simple. You have a bonding orbital that's lower in energy, an anti-bonding orbital that's higher in energy. And in general, whenever we're mixing together orbitals to make molecular orbitals, an important consideration to remember is that the number of atomic orbitals that we're combining will equal the number of molecular orbitals that are formed. So if we're combining two 1s orbitals like we are here, we'll get two molecular orbitals, one of them bonding, one of them antibonding in this case. All right. So that's how it works for the simpler case with just either 1s or any sort of s valence orbital would follow the same pattern. Only two energy levels to worry about, bonding at the bottom, antibonding at the top. So then what we're going to end up doing, though, with these diagrams is where we get the useful information is by populating them with the valence electrons. So then once we know, okay, how many valence electrons does our molecule or ion have, we start filling these molecular orbitals following the same rules that we learned for atomic orbitals. We fill lowest energy first, then go to higher energy. And in situations we'll see later where we have two orbitals at the same energy level, we fill those one at a time first before pairing them up. So all the rules that we learned for atomic orbitals still apply once we have a set of molecular orbitals to populate. So once we populate those molecular orbitals, we'll give those results here in a little bit. My notes are all messed up again. But anyway, we're going to get some parameters then that can be determined from the molecular orbital diagrams. So one of those is the bond order. So bond order we already talked about is single, double, or triple, bond order of 1, 2, or 3 typically, although we will see fractional bond orders in some of the molecular orbital diagrams we talked about. But the formula for that is once we populate a molecular orbital diagram, the bond order is going to be 1/2 times the number of electrons that are in bonding orbitals. So every time we put 2 electrons into a bonding orbital, that counts as 1 bond. So half of that gives you the number of bonds, half the number of electrons, minus the number of antibonding electrons. So every time we put 2 electrons in an antibonding orbital, we would cancel out one of the bonds. And so again, it's the difference between those two multiplied by 1/2 gives you the bond order. The other things that you can tell from a molecular orbital diagram are the bond types. So whether it's a sigma bond, a pi bond, or some combination. We learned from valence bond theory how to make that prediction, but sometimes those predictions are wrong, and the molecular orbital diagram gives us a different and often correct outcome. And then the other thing that we can determine from molecular orbital diagrams, which we introduced last time, is sort of the whole motivation for even needing a new bonding theory is correct prediction of and rationalization of the magnetic properties. So just as a quick review of that, really only two possibilities that you have to worry about. Diamagnetic, which is when you have no unpaired electrons, which means all of your orbitals are either doubly occupied with two electrons in them, or they have, or are completely empty in some cases, but you're never going to have singly filled orbitals. And when that happens, the physical properties that it would exhibit would to be weakly repelled by a magnetic field. The other possibility is paramagnetic, which is one or more unpaired electrons. For the ground states of diatomic molecules, like we'll talk about, there's only three possibilities. It's either diamagnetic with 0 unpaired electrons, or it could have 1 unpaired electron, or it could have 2 unpaired electrons. Those are the only possibilities you'll see. But if it has 1 or 2 unpaired electrons in our situation, or 1 or more in more general terms, in that situation, we would call it paramagnetic. And those substances, like we saw with liquid oxygen in the video I showed last time, are attracted to a magnetic field. So different physical properties with respect to how they behave in a magnetic field that can be predicted on the basis of the number of unpaired electrons. And the molecular orbital diagram, once it's correctly populated with electrons, will give us that information. All right. So now we're ready to start seeing how we can then make these determinations. So we start with the simple orbital diagrams for H2 and H2 plus, which are going to be just using 1s orbitals. So again, if we draw the full diagrams out, we're going to have 1s atomic orbitals on each hydrogen atom, and they're always going to mix the same way. It doesn't matter what the formula of the compound is or what the charge is, the orbitals will always mix the same way. So two 1s orbitals will form a bonding sigma 1s orbital that's lower in energy, anti-bonding sigma star 1s that's higher in energy. So that's what the orbital diagram will always look like. Then you just have to put the correct number of electrons in it to make any predictions about the properties that we just talked about. So H2 plus, we have to count the number of valence electrons like we've been doing for a while now. Hydrogen has one valence electron, so two hydrogens would have two valence electrons, but with a positive charge, you take one of those away. So H2 plus would just have one valence electron, one electron total, but it's a valence electron. So when we populate this orbital diagram with one electron, again, we start with the lowest energy orbitals and fill up. So you don't have to show the population of the atomic orbitals. I mean, technically speaking, if you wanted to, you'd have hydrogen combining with H plus to make H2 plus in the middle. But the part we care about and the part that gives us the information we want is this middle part of the diagram that shows the molecular orbitals. And again, one valence electron goes into the lowest energy available orbital, which is the sigma 1s. So that would be the electron configuration for H2 plus. It would be sigma 1s1 would be how we would write that configuration. And now we can predict the bond order. So bond order, as we said, is 1/2 times the number of bonding electrons minus the number of anti-bonding electrons. There's one electron is in a bonding orbital, and there's 0 electrons in the anti-bonding orbital. So 1 minus 0 times 1/2 is a bond order of 1/2. So this is the first time we would see a fractional bond order. We didn't really have that possibility when we drew Lewis structures before and used valence bond theory to predict things. But here we can get a fractional bond order of 1/2. Not likely a very strong bond, but one that we could at least theoretically predict as being a bond order of 1/2. So this I don't need anymore. Sorry. All right. And then if we go to the other side, here's H2. Now, if you were to draw the Lewis structure for H2, you would just draw it like that, which is very simple. Let's see if the molecular orbital diagram tells us the same thing. So the Lewis structure predicts that it's a diamagnetic molecule with a single bond. So does the molecular orbital diagram agree with that? In many cases it does, in some cases it doesn't, but let's see what the case is here. So exactly the same atomic orbitals available. Hydrogen each has a 1s orbital, so each hydrogen atom is 1s1. And then when those 1s orbitals mix, they're going to get a sigma and a sigma star. So you don't really have to draw out the whole diagram every time, as long as you remember that these are the molecular orbitals that are available. So when we fill this up with electrons, now H2 has a total of 2 electrons, 2 valence electrons, both valence, one from each hydrogen atom. And then we're going to populate sigma 1s, and that can have up to 2 electrons in it. So we populate it in that way. So again, the things that we learned for atomic orbitals are still valid here. You can put up to 2 electrons into each orbital. And if you do, one has to be spin up, one has to be spin down. So all that stuff we learned for atomic configuration still applies. We get this electron configuration here, sigma 1s2 is the configuration. And then for the bond order, what we see in this case is that now we have 2 electrons in our bonding orbital. So we're going to put a 2 there. Still 0 electrons in sigma star. And so 1/2 times 2 is a bond order of 1. So we predicted a single bond. Molecular orbit diagram is consistent with that. Molecular orbit diagram also tells us that it's diamagnetic because both of these electrons are paired. And that's also true for hydrogen. So relatively simple case, but one where the predictions sort of match our expectation. We'll talk more about the paramagnetic diamagnetic distinction later on. But one thing that's helpful to recognize is that if you're doing a molecular orbital diagram for a molecule or an ion that has an odd number of electrons, which is what we started with for H2 plus, that has to be paramagnetic. There's no way to have an odd number of electrons and have them all paired up. It's just not possible physically. So if your All right, I'm not muted anymore. Thank you for telling me. Would have been nice to know 15 minutes ago, but that's okay. I appreciate it. Oh boy. All right. Yeah, annoying. All right. Probably I'll check. I'll probably have to re-record the first part. All right, let me put a note for myself. It's easy for me to combine clips, so I'll walk through the first few slides again if I have to, and just combine it with what's coming after this. That shouldn't be too hard. Oh no, it was like for 1 second. Someone said that was only muted for 1 second. So I will. This side conversation is getting distracting, but I appreciate the commentary anyway. I will check it. Thank you for telling me. I don't know why I suddenly muted because I didn't press anything. So if someone in the live studio audience has the ability to mute me, please don't do that because I can't control it from here very easily. But I don't know what happened. If it was just for a second, I'll check the video at this stage and see what it looks like. All right. All right, back to the task at hand. So H2 minus is one that's going to now have the same exact orbitals available because we're still mixing hydrogen 1s orbitals. Only difference now is that we added an extra electron in, so that's going to be a total of 3. So then when we fill this with electrons, we go 1, 2, but we have no choice but to put our third electron up in the antibonding orbital. So again, we always completely fill the lower energy orbitals before moving our way up. In this case, after we fill the sigma 1s, we have to put it into sigma star. All right, so then when we look at the bond order for this, we already know it's paramagnetic because it's this odd number of electrons, but for the bond order, we have to do the quick calculation. This time we have 2 electrons in the bonding orbital still, so sigma 1s has 2 electrons in it. Sigma star has 1 electron in it now, so we have a 2 minus 1, which gives us, again, a bond order of 1/2. So H2 plus and H2 minus both have bond orders of 1/2 for a slightly different reason. But here, and keep in mind that when you're doing these bond order calculations, the two numbers that you're subtracting would add up to give you the total number of valence electrons. So it's just which portion of them are bonding, which portion of them are antibonding sort of goes into this equation here. And then finally for He2, which is dihelium. So you may be aware of the fact that the noble gases don't typically form bonds with themselves. So all the noble gases exist as just single atoms, helium, neon, argon, and so on. So does this tell us why that is? So if we go to He2, we still have 1s valence electrons from each helium atom. And we're still going to form the same molecular orbitals for He2, sigma and sigma star. But this time we have to populate with 4 total electrons. Each helium is atomic number 2, so each helium atom has 2 electrons. And so now there's a total of 4 for the fictitious diatomic He2 that we're working with. So when we populate this, we have 4 electrons. So 1, 2, that fills sigma 1s, and then 3, 4, we also have to fill sigma star 1s. So the bond order for this one, if it wasn't already obvious, we have 2 electrons in the bonding orbital, but we also have 2 electrons in the antibonding orbital. So those completely cancel each other out. We get a bond order of 0. Now, what does it mean to have a bond order of 0? Well, this means that the molecule is unstable and doesn't exist. So if you predict a bond order of 0, which is what would be the case for any of the noble gases, that's another way of saying that, well, the molecule doesn't exist. We kind of already maybe have some idea of that for noble gases, that they don't bond to each other, and this is why. When 2 noble gases come together and try to bond to each other, you end up filling both the bonding and the antibonding orbital, so there's no net bond, which means the molecule just doesn't exist as He2. It just falls apart into He atoms as it normally would be. All right, so that's going to be the case for the noble gas, and that helps rationalize why we don't see dihelium as a stable molecule anywhere, really. All right, so any questions so far on the simpler of the orbital diagrams that we've been doing? Yeah. Yeah, so each individual orbital would only have 2 electrons in it, just like we saw for atomic orbitals. We're going to get to a situation right now with p orbitals where you're going to end up having some degenerate energy levels that have 2 orbitals at the same energy. And in that case, each of those 2 orbitals gets up to 2 electrons. But there's always still a maximum of 2 electrons per orbital, just like we learned for atomic orbitals. All those sort of same quantum mechanical rules still apply to molecular orbital theory. It is a quantum mechanical bonding model, much in the same way as the electron configurations that we learned in chapter 2 come from quantum mechanics also. But good question. Anything else? All right, so if we move on to the p orbitals, the difference with p orbitals is that we now have 2 different types of molecular orbitals that can form. And so one of those is also sigma. So what we're going to assume here is that this is the way that general chemistry books do it, even though later on in your life you might change this, but assume that the bond axis, the direction of the bond, is the x direction. So what that means is that if we have 2 p orbitals directly pointed at each other in the x direction, so remember that the p orbitals, there's always going to be a set of 3, px, py, and pz. So the 2 that are oriented in the x direction right along the bond can combine in the same way that the 1s orbitals combine to make sigma and sigma star. So you have px combining in phase with px would allow you to make a sigma bonding orbital. So the way that would look is that you're going to have 1 p orbital, and we call x direction horizontal. So imagine that your bond is like this between 2 atoms A. So as that direction is the bond, you're going to have a 1 p orbital that looks like that. I'll show the nucleus in different colors so it's easier to see in this case. So there's your nucleus in red. So that's one of your px orbitals, and that's going to combine in phase with another one. Now, what it means to combine in phase in this case is that the lobes that are the same phase, the ones that are shaded the same, have to be pointing at each other. So remember that when we shade a p orbital like this, what it means is that the sign of the wave function is changing as we go from one side to the other. So it doesn't matter what you call positive and what's negative, but on either side of the nucleus, it changes from positive to negative. And so if we want to combine these 2 orbitals in phase, we need the 2 phases that are the same sign to be lined up with each other. So it would look kind of like this, where we take another identical p orbital, but now with the 2 unshaded lobes lined up with each other, or the 2 shaded is fine too, same story. And then when those combine to make a molecular orbital, they're going to give a sigma p bonding orbital, where you're going to have electron density in between the nuclei like that. But then because of these opposite phased lobes, you're going to have also some outside of the nuclei that are of the opposite phase. So your sigma p molecular orbital looks kind of like this. The overlap of the unshaded lobes is going to reinforce in the center as electron density between the nuclei. You'll have a little bit outside from the opposite lobes that don't overlap with each other, but that's what it would sort of look like. But again, it's an in-phase combination of two px orbitals that give you a sigma bonding orbital. And then now again, as we said, whenever two orbitals combine, so in this case, two px orbitals, they're always going to make an antibonding and a bonding orbital. So the bonding orbital is at the bottom, and the antibonding orbital will be above that in energy, so it's going to be sigma star. And that's going to be just, again, the out-of-phase combination of those same two orbitals. This time we're going to subtract the two. Subtracting two orbitals is the same as taking one of them and just flipping it over. So when you do that, you're going to have the two out-of-phase sections of the p orbitals lined up with each other, which means they're going to cancel out. They're going to destructively interfere if you think about it in wave terms. So what that ends up giving you is an antibonding orbital. A little bit harder to draw, but you're going to get a node in between the two once again, where you're going to have this sort of arrangement where, again, the opposite phases are now lined up with each other, so they destructively interfere, cancel out, and lead to mostly electron density now being outside of the nuclei. Again, a situation that would weaken the bond. So we call this, again, sigma star. And we put the little 2p, or just p in more general, I guess is fine. Not necessarily 2p. Sigma star p indicating that it's a antibonding sigma orbital that comes from p orbitals. Now that's pretty much in line with what we saw with 1s orbitals. Again, the shapes are a little more complicated because the shapes of the atomic orbitals are more complicated, but it's the same story. Head-to-head overlap, in phase makes a sigma orbital, out of phase makes a sigma star orbital. But we also have now two other p orbitals that we haven't done anything with. This is px, but we also have py and pz. So what happens with those ones? Well, those are also going to be able to form pi molecular orbitals. All right. So if we do it for, let's call this the y direction. So we can form a pi bonding orbital by in-phase combination of two py atomic orbitals. So what this looks like now is two orbitals that are not pointing right at each other, but that are aligned side to side. We talked about pi bonding already, so it does kind of line up with that picture that we've already developed in the context of valence bond theory. But again, if we have an in-phase overlap of two py orbitals, again, nuclei right at the center, I'll show them in red, what you get is a bonding pi p molecular orbital. And what that's going to look like is you're going to have your two nuclei there and there. And in this case, that electron density and that positive overlap is going to be sort of above and below where the nuclei are. So you're going to have a big lobe up here and another big lobe down here, opposite in phase from the two different lobes of the p orbital. All right. So again, it's a little bit different than we talked about in valence bond theory, because again, it's no longer two separate p orbitals overlapping side to side. It's a new delocalized molecular orbital that comes from side to side in phase overlap of those orbitals. But whenever we make bonding orbitals, we also make antibonding. So you have a pi star as well, which would be from out of phase combination of the two. So again, that's taking the same two orbitals, but this time subtracting them from one another. When you subtract orbitals mathematically, if you want to think about it graphically, that means you're taking one of them and flipping it over. And so when we do that, what we end up with is an antibonding orbital that looks kind of like this. You're going to have your two nuclei. I'll draw the bond axis to help me a little bit, but you don't necessarily have to have it there. But then what it looks like is sort of like this. All the electron density is now sort of outside where the nuclei are. And you get this sort of out of phase alignment of the two p orbitals like that. And that's your pi star. All right, so that's what happens with p orbitals I'm not going to try to draw it out because they look the same. They're just rotated 90 degrees, but the same exact thing happens with the PZ orbitals. So your PZ orbitals look exactly the same as this. It's just they will be rotated 90 degrees and pointing towards you. Harder to draw, of course, in that case. But again, Y vertical, the Z direction coming out towards you, still perpendicular to the bond axis. So it gives you the exact same types of orbitals, just oriented differently in space. And then those two sets of orbitals end up being degenerate with each other, the same energy. So the pi orbitals that form from PY are degenerate with the pi orbitals that form from PZ. And the pi star orbitals that form from PY are degenerate with the pi star orbitals that form from PZ. So you get two sets of degenerate orbitals, two bonding orbitals, and then two anti-bonding orbitals. So that same thing happens with PZ, and so you end up with, in total, two degenerate pi p and two degenerate pi star p molecular orbitals. Spelled degenerate, right? No, so that's what happens with the pi orbitals. And so that means when we have elements that are in the p block of the periodic table, so carbon, nitrogen, oxygen, fluorine, or anything below them, the molecular orbital diagrams end up being more complicated because you're going to have s valence orbitals, typically 2s if you're starting with that second row. And then those are going to make the sigma star. And then within the p orbitals, you're going to also have a set of sigma orbitals and sigma star and pi star. So it's more complicated, but the general outline is given. So this is what the orbital diagram would look like. So let's do it for O2 first. So remember that we introduced this topic last time by saying that O2 is paramagnetic, even though we wouldn't easily predict that from the Lewis structure. So let's see if the molecular orbital diagram for O2 predicts paramagnetic behavior. Okay. So let's talk about the diagram first before we worry about putting the electrons in. So we're going to, again, on the outside of the diagram, we're going to have the two atoms that are combining to make the diatomic molecule. The center of the diagram is going to have the orbitals for that molecule that are formed. So when we have oxygen, again, if we look at the periodic table, let me get that open for a second. So oxygen is over here in the 2p block of the periodic table. So as we discussed earlier in this course, around chapter 2 or so, the valence electrons for oxygen are the 2s and the 2p. So 2s2, 2p4, meaning that any of the elements in the p block are going to have both s and p valence orbitals available. And that's what we need to formulate for the molecular orbital diagrams. So we're going to have the 2s orbitals for oxygen involved in this diagram. And we're also going to have the 2p orbitals up higher in energy. Okay. So you'll recall that for 2p orbitals, you always have a set of three, as we talked about, px, py, and pz. So we're going to have three 2p orbitals from one oxygen atom combining with three 2p orbitals from the other. So we'll have a total of 8 orbitals, 4 atomic orbitals from each atom combining to make 8 molecular orbitals. So then what we look at is what happens then when we mix the atomic orbitals. The 2s orbitals are going to overlap, as we talked about already, to make sigma and sigma star, bonding at the bottom, anti-bonding at the top. And then we just also talked about it, pictorially anyway, what happens when 2p orbitals mix together. So the 2px orbitals that are along the bond are going to overlap head-to-head to make sigma interactions. So you're going to have sigma 2p and sigma star. And then in between those, you're going to have py and pz overlapping to make pi and pi star orbitals. And as we said, there's going to be 2 at each energy level because the ones that come from py and the ones that come from pz are the same energy, just rotated differently in space. So you're going to get your pi 2p here at lower energy, which is the bonding pi orbitals, and then pi star up here, a set of 2 for each of those. Now, one question that might come up is why is sigma 2p lower than pi 2p and why is sigma star higher than pi star? The reason for that, which is something we have not talked about up until this point, is that when you talk about how much does the orbital energy split when you make the bonding and anti-bonding orbitals, That's a function of how strong the overlap is between the two orbitals that are making those molecular orbitals. So sigma overlap, which is head-to-head right along the bond axis, is very strong overlap. So your sigma gets stabilized by a lot, and your sigma star goes up by a lot. And so that results in those being the lowest and highest. That side-to-side pi overlap is a bit weaker. And so when you form the bonding orbitals from those, they don't get stabilized as much, and the antibonding for those don't get destabilized as much. So that's why that ordering is like this. You get the largest splitting for sigma and sigma star, pi and pi star, intermediate. They still split, but not to the same extent. All right, so that's what the orbital diagram looks like for O2. Again, the most important thing to know, whether you fully understand all the details or not, is this is the correct order they come in. Sigma 2s, then sigma star, and then sigma and pi for the 2p, and then pi star and sigma star. Now we just have to go and populate those with the correct number of electrons to be able to make any predictions then about the properties. All right, so the first thing is, how many valence electrons does O2 have? We just looked at the periodic table. Remember, oxygen is group 6. So each oxygen atom has 6 valence electrons. There's 2 of them for a total of 12. So we're going to have to populate this orbital diagram with 12 valence electrons. So again, we go from lowest energy to highest energy. Each orbital can get up to 2 electrons before we move up to the next one. So for 12 electrons, we go 1, 2, 3, 4, 5, 6. Now, when we get to the degenerate orbitals, we pair them one at a time first. So we go 7, 8, 9, 10. That gets completely filled. We still have 2 more electrons, so we're going to go 11 and 12. Okay? So the last 2 electrons we put in are up here in the pi star orbital, pi star 2p orbitals. Because they're 2 degenerate orbitals, they each get 1 electron. Let me make that label a little bit smaller. All right. And then what we can see now, because of these 2 unpaired electrons, that would lead to the prediction that O2 is paramagnetic, which is in fact what it is, as we saw in the video that I showed last time. So this bonding theory for O2 matches the experimental data much better than we would get from valence bond theory. I think that deserves an exclamation point. I'm stingy with exclamation points, but I think that's pretty cool. So that's again, some confirmation that this bonding theory is likely more accurate, and it does predict the paramagnetic behavior of O2. We can also calculate the bond order, as we said. So it starts with a 1/2, and then what we do for bond order is we take first the number of electrons that are in bonding orbitals. So there's 12 total electrons in oxygen, O2. So how many of those are in bonding orbitals? We have the 2 down here in sigma 2s, 4, 6, 8. So all of our bonding orbitals are filled. So there's a total of 8 electrons in bonding orbitals. Of the 12, there should be 4 that are antibonding. So there's these 2 here that are in sigma star. That's 2 antibonding electrons, and then 2 more up here in pi star. So a total of 4 antibonding electrons. 1/2 times 8 minus 4 is 2. So we predict a double bond for O2, which is what you would draw if you sketch out the Lewis structure. So that's not in contrast at all. And then we might also ask you for the electron configuration of O2 from the molecular diagram. So you would write that as something like this: sigma star 2s2, sigma star 2s2. This is just, again, like we write electron configurations, each energy level with how many electrons are in it. So 2 electrons in sigma 2s, 2 electrons sigma star. Sigma 2p has 2 electrons in it. Pi 2p has 4. You might sometimes see the 2 pi orbitals separated, but that's not really necessary to do. Just write it as pi 2p4. There's 2 pi orbitals with a total of 4 electrons in them. And then pi star 2p finishes up with 2 electrons. So that would be the correct electron configuration for O2. 12 total electrons. This is the energy levels that they are divided up into. All right, so that's how it works for molecular order diagrams for the 2p elements. Now, I want to be clear, I didn't mention this at the beginning. This specific diagram, this ordering of molecular orbitals, applies only to the second half of the p block. So starting with O2, which is p4, P5, which is F2, or if you want to do it for neon, which is the last one in the P block, you get the exact same ordering that I'm showing here. But when we go to the first half of the P block, there is a switch that occurs. Before I do that, let's do the rest in that series, though. So If we go to F2, it's the same exact diagram. So let's just practice doing this now. Again, you don't necessarily have to write out all of these details if you don't want to, once you get familiar with this, but we're going to start with 2s and 2p atomic orbitals from each fluorine atom, and they're going to combine to make molecular orbitals for F2, same exact diagram that we just drew. So the 2s orbitals combine to make sigma and sigma star. Again, the middle part of the diagram is really the important part for you, and then we're going to have sigma 2p, pi 2p, and then pi star and sigma star, the antibonding orbitals up here. All right. So all that's left now for F2 is just to populate it with the correct number of electrons. And so for F2, we go over, and it's just 1 over from oxygen. So fluorine is group 7, so there's 7 valence electrons for each one, total of 14. So this diagram, we're going to populate with 14 electrons to correspond to the valence electron count for F2. And then what we do is, I guess I didn't draw out you don't have to do this. If you were wondering why I didn't, I just forgot. Again, that's the atomic configuration for each oxygen atom. You don't have to include that at all, but that's what it will be if you wanted to include the atomic configuration. Again, what we care about the most is the middle part of the diagram. For fluorine, it's 2s2, 2p5 atomic configuration, which you don't need to worry about as long as you have the correct number of electrons. But that's what the atomic configurations look like as a review. And then when we populate the molecular orbitals, again, we're going to take all 14 of these electrons and dump them into these molecular orbitals from lowest to highest in energy. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in this case, we just add those 2 additional electrons into pi star 2p as well and completely fill it. So we will predict that fluorine is diamagnetic. We will predict the bond order to be, we have 14 electrons this time. We still have all 4 of our bonding orbitals filled, sigma 2s, sigma 2p, and pi 2p. So a total of 8 electrons that are in bonding orbitals. Now we have 6 that are antibonding, 2 from here, 2 more from there and there. So that's a total of 6 of our 14 are antibonding. So we get a bond order of 1. So we predict a single bond for F2, and an electron configuration would be sigma 2s2, sigma star, 2s2. The sigma 2b orbital has 2 electrons in it. Pi 2p has 4. Pi star 2p also has 4. So you can, again, this is the way that we might ask some of these questions on homework assignments, where you can write out the full configuration that specifies the population of each orbital energy level. Now, if we drew the Lewis structure for F2, we would predict this, which is a single bond with a dimagnetic arrangement of electrons. So we don't really get any new information from like orbital diagrams. So there are some times when the information that you would get from the Lewis structure is identical to what the molecular orbital diagram gives you, but in other cases, like we saw for O2, there's a bit of a divergence there. So the molecular orbital diagram is the more authoritative way of thinking about how equivalent bonds form in molecules. All right, so that's F2, and then just to finish this off, Ne2. As we said already, with the example of dihelium, we don't expect noble gases to form bonds with each other. Let's see if the orbital diagram rationalizes that. So each neon has, again, 2s and 2p valence orbitals. So the molecular orbital diagram looks the same exact ordering and everything. It would be different energy. We're not worried about those sort of considerations. A completely filled 2s and 2p orbitals if we go to the noble gas column, starting with neon. All right. So that's going to be the atomic configuration of each neon atom. So when they make dineon, you will get the same molecular orbitals that we have already seen twice. That should be 2p. And then this time we have a total of 16 valence electrons. Each neon atom is 2s2, 2p6 valence configuration. 8 electrons each for a total of 16. And now we're going to end up filling all of these. 2, 4, 6, 8, 10, 12. Sorry, 2, 4, 6, 8, 10, 12, 14, 16. So we fill up all of the molecular orbitals. So when we calculate the bond order for this, 8 of our 16 electrons are in bonding orbitals. 2, 4, 6, 8. Those are orbitals that don't have stars next to them. But we also filled up all of our antibonding orbitals with 8 electrons. 2, 4, 6, 8. So all the orbitals with stars next to them have electrons in them as well. So we get a bond order of 0, which, as we said before, means this is an unstable molecule that wouldn't exist. All right, so further confirmation that the noble gases don't like to bond to each other for this reason. You end up filling up all the molecular orbitals, all of your bonding orbitals and antibonding orbitals, so all the bonds get canceled out, and there is no bond holding things together. All right, so any questions on those diagrams? All right, now, as I said, the ordering that I'm showing here applies specifically to the second half of the P block. When you go to the first half of the P block, there is one key difference that you have to remember, which would not affect the calculation of the bond order, but it would affect the calculation of the magnetic properties in some cases. So we have to be aware of that. All right, so if we go to the first half of the P block, boron, carbon, nitrogen, P1, P2, P3 for their valence configurations, what ends up happening is we still have the same valence orbitals available. So if we're doing diboron B2, boron atoms, you have 2s and 2p valence orbitals. So same exact atomic orbitals mixing together. And you're going to form the same molecular orbitals as well, but there's going to be one place where the ordering switches that we have to be aware of. So sigma and sigma star 2s are still the same. But when we get up here to the 2p molecular orbitals, what ends up happening is that the pi 2p molecular orbital comes below sigma 2p. So these are the two that switch. So I'll finish this up and then I'll draw a box around that to show you. The ordering of these two molecular orbitals here switch for that first half of the P block. So diboron, dicarbon, dinitrogen. Again, the P1 through P3 blocks of the periodic table. All right. For your purposes, you mostly just have to remember that that happens. And again, especially if you're trying to calculate the magnetic properties, that can be important. Why it happens is more complicated and not something you have to worry about. But for those of you that are curious enough to want to know, basically the situation is that when you're forming molecular orbitals, there's no rule that only 2s orbitals can mix with each other and only 2p orbitals can mix with each other. Any orbital that's sigma in nature can mix with any other orbital that's sigma in nature. So what happens in these elements is that as you go left to right across the P block, the energy gap between the 2s and 2p orbitals gets larger and larger. So in the second half of the P block, 2s and 2p are far apart in energy, so they can't mix with each other at all. Orbitals have to be relatively close in energy to mix. But for the first half of the P block, boron, carbon, nitrogen, even though I didn't necessarily indicate it clearly in the diagrams, the 2s and 2p orbitals are kind of closer together. And that means that these sigma orbitals are no longer purely 2s or 2p. You're going to get some contribution of the 2p orbitals down to this sigma star, some contribution of 2s to this one that sort of pushes it up in energy. And so basically you get what's called sp mixing. Again, you don't have to be, you're not responsible for that reasoning, but it's because of the closer proximity of these orbitals in terms of energy. More mixing between S and P sort of perturbs the energies and the ordering of those orbitals. You just have to mainly remember that it happens. All right. So for B2, then we're gonna have 6 valence electrons because boron is 2s2, 2p1 valence configuration is group 3. So there's a total of 3 electrons from each boron atom, a total of 6 then that go into our diagram. So when we put those in, we have to go bottom to top still. So we go 1, 2, 3, 4, 5, and 6. So this ends up with 2 singly occupied pi 2p orbitals. So we predict a paramagnetic ground state. And then the bond order for this would be, we have 6 total electrons. 4 of them are in bonding orbitals. These two down here in sigma 2s. These two up here in pi 2p are all in bonding orbitals. The other two, the two that are in sigma star, are antibonding. So we get a bond order of 1. Although if we look closely at the electron configuration, so valence bond theory would have said, okay, it's a single bond, it has to be a sigma bond. If we look at the valence electron configuration for this guy, though, we get sigma 2s2, sigma star 2s2, and then our last two electrons are in the pi molecular orbital. So what ends up happening is that the sigma and sigma star 2s orbitals basically cancel each other out. There's no net sigma bond. The only net bond that we have is a pi bond. So this is a single bond, but we predict that it would be a pi bond, not a sigma bond. So that's another difference you sometimes see. We don't tend to ask a lot of questions about that, I suppose. But that's another distinguishing feature of molecular orbital theory versus valence bond theory. Valence bond theory would have said, if the bond order is 1, it has to be a sigma bond, and that's as simple as it gets. But for molecular orbital theory, there are situations, especially when you flip the ordering of these two orbitals here, that you can get a single bond, but it's actually a pi bond, because again, sigma and sigma star cancel out. The net bonding orbital is going to end up being pi in nature. All right, so that's B2. If we go to C2, dicarbon, again, we flip the order of those two orbitals. So same exact orbital diagram. So quickly label it. 2s and 2p atomic orbitals for carbon, 2s2, 2p2 for each of those valence configurations. And then we're going to form dicarbon that's going to have a sigma 2s and a sigma star 2s first. Flipping the ordering of these two, so we get pi and then sigma for the 2p's. And then the ordering of these always stays the same, pi star and then sigma star, okay? All right, so that's the ordering for dicarbon. This time we have 8 total valence electrons, 4 from each carbon atom. So when we populate this with electrons, we get 1, 2, 3, 4, 5, 6, 7, 8. So this one we predict is diamagnetic, because all of the orbitals are doubly occupied, all the electrons are paired. The configuration is sigma 2s2, sigma star 2s2. Those two are typically always filled. And then our last 4 electrons went into pi 2p. Bond order. We have 8 electrons in carbon. 6 of them are in bonding orbitals. These 2 in sigma 2s and the 4 that are in pi 2p. All 6 of those electrons are in bonding orbitals. And then we have the 2 from sigma star that are antibonding. So 1/2 times 6 minus 2 is a bond order of 2. So we predict that this is a double bond for C2. But the prediction we would make about the types of bonds are, once again, sigma and sigma star. That bonding and antibonding combination cancels out. So we're left with 2 filled pi orbitals, meaning that we have 0 sigma bonds and 2 pi bonds in C2. Valence bond theory would have said, well, it's a double bond, so it's one of each, 1 sigma, 1 pi. But from the molecular orbital diagram, this is not really a common or stable molecule, as it turns out. But the molecular orbital diagram will predict that it's actually 2 pi bonds being formed, because the sigma orbitals and sigma star are both filled. The only net bond comes from the pi orbitals. So again, some different predictions we can get. The important things are the magnetism, the configuration, the bond order. We're not going to ask you too much about bond types, but you should be a little bit familiar with it. But that's what we get for C2. And then finally, if we go to N2, last one we'll do, we could draw a Lewis structure for N2, and we end up with a triple bond. Sigma and 2 pi's. Let's see if the molecular orbital diagram makes that same prediction. N2 is a nice stable molecule. We see it all the time. It's 80% of our atmosphere. So let's see if the molecular orbital diagram matches what we expect from just the Lewis structure. So when we do N2, we have the same exact ordering of orbitals. Because it's in the first half of the p block, we're going to have that switching of the orbitals for the bonding 2p set. So sigma and sigma star always start us out. But then here's where the pi 2p comes before sigma, as we said, for the first 3 elements in the p block. And then pi star and sigma star at the top, which never get filled for these ones, as it turns out. All right. So nitrogen has a 2s2, 2p3 valence configuration. So 5 valence electrons from each nitrogen atom. and then a total of 10 that would go into our molecular orbital diagram. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we end up filling up sigma 2p in this case with our last 2 electrons. So we predict a diamagnetic ground state, which the Lewis structure would have also predicted for us. And then we predict a bond order, in this case, of 1/2 times, this time we filled up all 4 of our bonding orbitals. So we have 2, 4, 6, 8 electrons that are in bonding orbitals. Only 2 that are in the sigma star that are anti-bonding. So we do predict a bond order of 3, which is a triple bond, and a configuration then that would come out as 2 electrons in each of the sigma and sigma star orbitals. And then we have our bonding pi 2p is filled with 4 electrons, 2 orbitals, each with 2 in it. Then our sigma 2p has the last 2 electrons in it. So nothing really, again, surprising about N2 that comes from the molecular order diagram. Diamagnetic triple bond, 1 sigma, 2 pi bonds, exactly what we would predict from the valence bond theory. All right, so that I think takes us to through all the neutral 2p molecules. So a little bit repetitive, but hopefully you kind of see the process now and how it works. The very last one I'll do is, again, a situation where we can have fractional bond orders. Now, you only will see fractional bond orders, meaning a bond order of something 0.5, if you have an odd number of electrons. So if there's an even number of electrons in your molecule, in the ground state, you would expect the bond order to always just be 0, 1, 2, or 3, a whole number. But when you have odd numbers of electrons, you're going to have fractional bond orders, and that's the case with N2 plus. So N2 plus is just 1 electron different than N2, so you just take off 1 electron. We're going to formally mix an N with an N plus to make N2 plus. Again, the outside part of the diagram, not that important for us, but if we want to be complete, we'll fill it in. So nitrogen was 2s2, 2p3. Nitrogen plus just has 1 fewer electron. And so we're going to have a total of 9 electrons to put into this same set of orbitals. Sigma and sigma star for 2s. Pi and then sigma for 2p, and then pi star and sigma star. Now, if you're doing anions or cations that are based on the p block elements, without any additional information given to you, you would assume that the ordering of the orbital stays the same as it would for the neutral molecule. So N2 has this ordering of its molecular orbitals, again, with these 2 being the ones that switch relative to the other ones. And so for N2 plus, we would assume that's the same. If there are ever ambiguous situations where it's not clear what order the orbitals come in, we'll specify that for you. But in most cases, it's going to, again, just be based on the elements that are involved in that molecular ion. So we have 9 electrons to put in here. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. So the only difference is that we have a singly occupied sigma 2p. So our configuration just ends with 1 electron in the sigma 2p. So 2 each in those. Still a filled pi 2p set, and then now with just 1 electron in sigma 2p. And the bond order would be 1/2, and then we have, in this case, 7 electrons that are bonding. These 2, 4, 6, and then 1 more in sigma 2p. So 7 electrons that are in bonding orbitals. Still just the same 2 sigma star electrons that are anti-bonding. So 7 minus 2 is 5 times 1/2 is a 2.5 bond order. All right, so again, if you have odd number of electrons, you can expect a bond order that's fractional, something 0.5. So that takes us through really all the major possibilities for just the simple diatomic molecules. You might occasionally see problems where you have 2 different elements like CO, carbon monoxide. In that case, again, we would specify the ordering if it wasn't clear from the problem or if it mattered, but you'd still populate them the same way. Now, some patterns that are helpful to recognize as you do this, because it seems complicated, and in reality it kind of is, but the types of stuff we're going to ask you are typically pretty straightforward on this. It's going to be, again, filling in the orbitals with the correct number of electrons, and then asking some question about the electron configuration, the bond order, or the magnetism. So if the molecule has an even number of valence electrons, which will be true for all the neutral molecules, and also some of the ions as well, if they're doubly charged, if you have an even number of valence electrons, you would expect a whole number bond order, typically 1, 2, or 3, or 0 if it's unstable, but a whole number bond order, But the magnetic properties, it could be diamagnetic or paramagnetic. You can't predict that from just the number of electrons in the formula, okay? So for even number of electrons, it's going to be either diamagnetic or paramagnetic, and you have to populate the orbitals correctly to make that prediction. It will have either 0 unpaired electrons, which is diamagnetic, or 2 unpaired electrons if it's paramagnetic. For ions like this, or anything that has an odd number of electrons, the situation ends up being much simpler. First of all, you'll know that you're going to have a fractional bond order of something 0.5. Again, what that number is comes from the correct population of the orbitals. But you will also know, without any other additional analysis, that anything with an odd number of electrons is going to be paramagnetic and is going to have exactly 1 unpaired electron. So there's some shortcuts you can take the more that you do this. So look for those patterns. But again, understanding how to populate these orbital diagrams is going to be particularly important for us. All right, so any questions on that before I move on to the last couple of quick topics? All right, now the last thing that this chapter in your book covers is the idea of how do we use molecular orbital theory on something that's much more complicated than just two atoms bonding together. Now, we're not going to go through the details of this, but just like a really quick introduction to how molecular orbital theory works for larger molecules, and to give an idea again of the value and sort of the importance of having this sort of delocalized bonding theory. So for this, we can consider the organic molecule benzene. I forget how many years ago this was. Most of you were probably still like in elementary or middle school. There was a benzene leak one time recently in the Houston area, so got a lot of news coverage. It's a pretty toxic substance, but it's a molecule that looks like this. So to draw the structure of benzene, it's a ring of 6 carbon atoms. So it's a ring of 6 carbon atoms. Each of them has a hydrogen on it. It's outside the ring. And then to make sure the octets of every carbon atom is complete, you would need to have in the structure a double bond alternating like that. So alternating single and double bonds around that ring. Now, what you should maybe recognize is that there are 2 resonance forms for benzene. So I drew the double bonds here, here, and here, but I could have also drawn them in the alternating positions. It would have been equally valid. So there's 2 equally contributing resonance forms for benzene, where you just move those double bonds around to the alternate possible positions. So that would be putting double bonds here, here, and here. So there's 2 resonance forms of benzene where the double bonds change their positions. Now, the way that you want to think about this, though, as we talked about with resonance forms, you don't want to think about it as, well, there's alternating single and double bonds, and sometimes the double bond's here and sometimes it's there. That's not really what resonance is telling us. Resonance is telling us that those double bonds, instead of being localized between 2 carbon atoms, are completely delocalized over the entire ring. So the way that you can sort of draw that, and sometimes done, is you'll have your ring of 6 carbon atoms. The hydrogen's all on the outside that we don't really need to worry about too much. But you'll sometimes see this drawn with just a big circle in the middle of the ring, which tells you that those pi orbitals, those pi electrons that come from the double bonds, are delocalized over all 6 positions equally. Again, not alternating or not, sometimes here, sometimes there. They're completely delocalized. And so what that means is that all of the carbon-carbon bonds are in equal length. So they're between a single and double bond. So sometimes they're drawn as sort of like this with a dash line. But however you sort of formulate that, all those bonds are equal in length. They're in between a single and a double bond, but there's no difference between them. And if we think about it in the context of valence bond theory, all the carbon atoms are sp2 hybridized. Because whichever resonance form you consider, each of the carbon atoms has 3 electron groups on it. It's bonded to 2 neighboring carbon atoms in the ring, and also then to the hydrogen atoms outside the ring. So each carbon is sp2 hybridized. Now, what is sometimes useful to do in the context of larger molecules like this, you'll kind of, this is a bit of a preview of some stuff you learn in organic chemistry if you go that far. What sometimes is useful to do is to actually consider sort of a mix of valence bond theory and molecular orbital theory. Even though molecular orbital theory is the the more correct and more rigorous bonding theory that we covered, it's a lot more complicated than valence bond theory. And valence bond theory still is useful and helpful sometimes. So what you'll sometimes see is in a situation like this, we could say, okay, well, the sigma bonds in benzene, we can pretty easily sort of model those or formulate those with valence bond theory. So we said that each carbon atom is sp2 hybridized. So each carbon atom is going to have a set of sp2 hybrid orbitals that make a trigonal planar arrangement. And this is the diagram I have to draw that really tests my limited artistic ability. So I'm probably going to screw this up a few times. So each carbon atom is sp2 hybridized. There's one there. There's one. I'll put the carbon atoms in red maybe to help see this. So the each carbon atom is there in the ring. It's going to be distorted. I apologize for that, but failed kindergarten for having bad motor skills. So I'm even pretty proud that I can draw this well. So, all right. And then, all right, not too bad. All right, so each of the 6 carbon atoms, which I'm going to highlight in red where the sort of central positions are, has a set of identical sp2 hybrid orbitals. And what happens then, I didn't draw it perfectly, but around the ring, those sigma bonds are going to be formed between the 2 carbon atoms by overlapping of those sp2 orbitals. These ones I probably can do a little bit better job of, like there, there, and there. But around that ring, you have adjacent sp2 orbitals on each carbon atom. They're going to overlap to form the sigma bonds between carbons. And then outside the ring, you're going to have a 1s orbital from hydrogen that's going to overlap with each of those exterior facing sp2 orbitals. So a 1s orbital from each of the hydrogen atoms outside the ring that overlaps with the remaining sp2 orbital to make the CH sigma bonds. So this accounts for all of the sigma bonds in this molecule. So again, if the picture is not entirely clear, basically what you have is the sigma bonds formed by 2 adjacent sp2 orbitals overlapping in the ring. So that makes all of your carbon-carbon bonds. Or the CH bond, the remaining sp2 orbital is going to overlap with a 1s orbital from hydrogen. All right, so again, each carbon is sp2 hybridized, so it has 3 hybrid orbitals. 2 of them overlap with neighboring hybrid orbitals to make carbon-carbon bonds. 1 of them overlaps with the exterior hydrogen atom to make that bond outside the ring. So again, sometimes it's easier to think about bonding in context of valence bond theory. So that works well for the sigma bonds. But then for the pi bonds, it's more useful to think about it in terms of the delocalized molecular orbital theory. So we're not going to go through all the details on this, but basically what happens in benzene is that if you think about the carbon atoms that make a hexagon, so each of the vertices here is a carbon atom, and we'll do that in red too, so you can see it more clearly. So you have a carbon there, carbon there, carbon there, carbon there, carbon there, carbon there. Now, we just talked about how each of those carbon atoms is sp2 hybridized and is going to use its sp2 orbitals to make all the sigma bonds that are there. But if an atom is sp2 hybridized, remember that it also has 1 unhybridized p orbital. So each of these carbon atoms, in addition to the 3 sp2 hybrid orbitals, is going to have 1 unhybridized p orbital. It's going to be perpendicular to those sp2 orbitals. So you're going to have a p orbital on each carbon atom, perpendicular to the 6-membered ring. And if they're all lined up with the same phase, you can have overlap above the ring and below the ring from those p orbitals. And that's sort of what this diagram shows here, is that when the p orbitals overlap, they form these delocalized molecular orbitals. This is the one that's lowest energy. There's going to be a total of 6 because there's 6 p orbitals. They're going to overlap to form 6 molecular orbitals. But the one that's lowest in energy looks like this, where it has in-phase overlap of all 6 of those p orbitals. So again, molecular orbital theory allows us to formulate orbitals that are delocalized over an entire molecule. We're no longer restricted to having just two adjacent atoms with overlapping orbitals making a bond. We can have orbitals that are delocalized over much larger regions. And in benzene, the pi orbitals are delocalized over the entire ring. This is the lowest energy orbital, and there's some higher than that, and you end up filling up all the bonding orbitals, and that leads to those free pi bonds that you would have in benzene. So you're going to have, just to sort of summarize that verbally, delocalized pi molecular orbitals, which are going to be formed by mixing or overlap, if you like that word better, of the unhybridized 2pz atomic orbitals. Those are the ones that are left unhybridized in each carbon sp2 hybridized set, and those are going to be available for that pi bonding above and below the ring. So again, we don't have to get into a lot of the details of that. It's beyond the scope of this course, but your book kind of has a section of that I wanted to cover briefly about the idea that molecular orbital theory can be used to describe delocalized orbitals over larger ranges and sort of help us understand a little bit better about what resonance refers to. Any last questions before I wrap up? All right, so we're going to transition a lot on Wednesday with a much more quantitative look at things in chemistry. So this takes us to the end of sort of a more theoretical part, and we'll see you then to start that.